right. Do you want to lead us off, Rochelle, or should I?
You can go ahead.
Okay. Welcome to the third episode of season 1 of the AAPG Salt Basins webinar series. So far, we've had a great couple of talks before this, and you can catch those on the YouTube site. Maybe Rochelle could provide links to our AAPG webpage, please, in the YouTube site. If not, I can do it after the introduction here of Conor. But today, we have a great talk that I'm really excited about myself from Conor O'Sullivan, who you can see right there, with the headphones on. He'll be speaking about multi-layered salt systems on the Irish Atlantic margin, their role in basin evolution, natural gas exploration, and future CO2 storage. A little bit more about Conor. Conor is a PhD researcher at University College Dublin of Earth Sciences, the Fault Analysis Group, and iCRAG Center. I'm sure he'll tell you what that stands for. His research focuses on the structural evolution of the Slyne and Erris basins offshore Northwest Ireland, with an interest in structural inheritance and the role salt plays in the evolution and implications for natural gas exploration and the future of CO2. He's worked with explorers refining the understanding of the multi-phase structural evolution of the Irish Atlantic margin. Conor has a BSc in Geology and an MSc in Petroleum Geoscience from Imperial Royal School of Mines. Conor's research is funded through a grant from Science Foundation Ireland and is part funded by the European Union Regional Development Fund and by the Petroleum Infrastructure Programme and its member companies. And without further ado, Conor, thank you for coming to present to us today, and I'll leave the floor to you.
Thank you very much. If the host can enable screen sharing, that'll be good to go. There we go, lovely. Let me just move this out of the way. Lovely. So, yeah, thank you all for coming today, and thanks for the introduction there, Tim. Much appreciated. Yeah, I'll be talking today about multi-layered salt systems on the Irish Atlantic margin and why they're important for things like natural gas exploration and CO2 storage. So just before we begin, I'd like to thank my supervisors, particularly Conrad and Mudis are there, as well as all the lovely people at iCRAG. You can see in the picture there in pre-social distancing times, having a great time together. And then just a list of different people on the bottom there that have contributed in some small way, be it 5 minutes at a poster session or coming over to UCD, looking at the data, having a chat, or working with them through our industry contacts. So big thanks to those people. And then just to acknowledge the funding bodies, the organizations that have provided the data that is used in the study, and of course the software vendors who provide the software that lets us do the research that we do. So a quick overview of today. It's going to be a relatively simple presentation. I'm going to walk you through how we get a better understanding of the distribution of salt on the Irish Atlantic margin using both well and seismic data. And following that, I'm going to give you a little tour through the basin, and then we're going to look at 2 salt-related structures in particular in these basins that are quite unique and quite interesting, and have a little look at how they develop and how they might be important CO2 storage sites in the future. So just before we begin, as Tim alluded to, so iCRAG is it's an applied geoscience research center, so we like to look at the societal implications of our research and the rationale of why we do it. So salt tectonics, for some reason, is poorly understood offshore Ireland, even though we have encountered it in several wells, and it is known to play a key role in existing gas discoveries on the Irish Atlantic margin. Nevertheless, its distribution and composition remain uncertain until today, hopefully. And then the societal impact of what we do, essentially, if you look at the graph on the right, which is a fuel mix for Ireland's electricity generation from last year, natural gas still plays a very large role in the electricity generation in Ireland, in particular during the summer months. And while Ireland is growing its renewable energy base, especially moving now into offshore wind, for the near future, natural gas is likely to play an important role, and so there's a good impetus to find further gas resources offshore Ireland. Looking further into the future, these same structures that will contain gas deposits will also make excellent storage sites for sequestered CO2. So in understanding them today with the context of finding more gas to keep the lights on, they can also play a role in the future when we start to really capture CO2 and draw it out of the atmosphere. So for those unfamiliar with the Irish Atlantic margin, it is very big. The offshore area of Ireland is 10 times the size of the island of Ireland. And as you can see from the map on the left, which is colloquially known as the real map of Ireland, this offshore area covers shallow shelfal areas, deep troughs like the Rockall and Porcupine troughs, and extends as far west as the Atlantic Abyssal Plain. Now, beneath the seabed offshore Ireland, if you look at the map on the right, it's essentially underlain by a framework of rift basins that represent a series of failed rifts that predated the eventual opening of the Northwest Atlantic during the early Eocene. And some of you are probably familiar with the more well-known ones, like the Rockall Basin, the Porcupine Basin, and the Celtic Sea basins. But as you can see today, we're going to focus on two basins off the northwestern coast of Ireland, the Slyne Basin and the Erris Basin. So a very quick introduction to these basins. As the map shows you, they are essentially a very narrow, contiguous series of interconnected grabens and half grabens, and they have a complex multi-phase structural evolution. Rifting begins in the late Permian and is followed by subsequent rift phases during the early Jurassic, and then the main phase of rifting, which occurs in the late Jurassic. Rifting stops then at the end of the Jurassic, and the entire area experiences kilometer scale uplift during both the Cretaceous and the Cenozoic. So we're removing a lot of stuff off the top of these basins. At the same time, we're getting influence from the North Atlantic Igneous Province. So we get numerous cells intruding throughout the stratigraphy throughout the area. And we get the extrusion of lavas of the Druid Formation, particularly in the northern Slyne area and throughout the Erris Basin and down into the southern Slyne. The biggest influence on the post-rift development of these areas is, of course, the Rockall Basin to the northwest, this big, huge, hyperextended basin. And it affects it in two ways. So during the Cretaceous, which is the main phase of rifting for the Rockall Basin, because particularly the Erris Basin sits on the flank of this large hyperextended basin, it undergoes a lot of rift shoulder uplift. So the western margin of these basins experience a lot of uplift during the Cretaceous as the Rockall is developing. And then when rifting ceases at the end of the Cretaceous and we get this post-rift thermal subsidence, we then get a lot more subsidence along the western margin then of these basins, which were previously uplifted. Now, where does salt fit into all of this? Well, there are two main layers that I'm going to focus on today. The first of which is the Upper Triassic Ullin halite member, which belongs to the Corrib Formation. And that's essentially an equivalent of the Kuiper group that would be relatively common across northwestern Europe. And then the second is the Upper Permian Zechstein group, which is a world famous salt giant present across a lot of Europe. Now, what's interesting in this basin is we also see salt in other parts of the stratigraphy. So in the lower Jurassic, in the Mila Formation, we get salt occurring locally within the basin. And also in the Mississippian and the lower Carboniferous, we locally get salt developing in the Tornasian section there as well. So there are areas in this basin where you can actually have stacked on top of each other 4 discrete layers of salt within the stratigraphy, all autochthonous. So it's quite a salty basin. There might not be a lot of it, but it's there throughout the stratigraphy. So now that we know what we're looking for, how do we actually understand the distribution of the salt offshore? So our first port of call is, of course, downhole borehole data. Now, because northwestern Ireland is a relatively underexplored part of the world, these well penetrations are few and far between. So as an example, in the Permian section, when we're going to be investigating the Zechstein group, we only have 5 wells across the entire study area, which is less than about 1 well per 1,000 kilometers squared. And we're looking at an average of 55 kilometers per well penetration. So to back up this relatively sparse data set, we're going to rely on a much more extensive seismic database. Now, this is a big multi-vintage database with 2D lines from the 1970s, right up to 3D OVC surveys acquired in 2013. So it is variable in its quality. And as I mentioned previously, those Eocene lavas that we see throughout the study area, they really impact the seismic data locally where they occur. So we'll see that a little bit later on. And then on the seismic data, we're looking essentially for the distinct markers of salt. So we're looking for mechanical detachment of the sub and suprasalt sections, and characteristic salt-related structures like salt pillows, salt diapirs, and even salt rollers. So we'll keep an eye out for those as we go through the basin. So I'm first going to show you well sections through both the Permian and the Triassic section, first of which will be the Zechstein group here in the Upper Permian. So if you look at this well correlation from south to north, you can see broadly that our salt content is decreasing as we go northwards. So in the very south of the study area, in the central Slyne Basin, we get over 200 meters of a very clean halite. You can see the core there is sort of a white to salmony pink, massive crystalline halite. There's some pattern salts at the top there, which are giving that jagged profile at about 1440 meters below rotary table. And then at the base, we're getting anhydrite. But as we're moving north, we lose the salt, particularly as we move into the Erris Basin. And we're looking at meter scale stringers of anhydrite in a background of predominantly clastics and carbonates. What's also interesting to note here, if we look at the seismic wavelet adjacent to the 1951 well, that's a seismic section that goes, that's a seismic line that goes through that well. In this area, the Permian, because it's only about 20 meters thick in the wells, it is essentially subseismic. So where we lose the big thick salt content, it's going to be very tough to actually map this quite thin, essentially veneer of Permian that we find throughout the study area. So it's just something to bear in mind. Now, if we look at the Triassic well section, we can see we have a lot more well penetrations. This is because the primary reservoir in the area is the lower Triassic Corrib sandstone formation. So a lot of operators, once they get there, happy days, stop drilling. And what we can see here is that this salt, this ill and halite member that's in this upper Triassic section is concentrated in the northern Slyne area as far as the well penetrations are concerned. It also extends into the southern area, southern Erris, based on the seismic data. And what we can see is that the halite section for the ill and halite member is not as clean as it is for the Zechstein group. So we're getting a lot of these interbedded red mudstone layers, particularly in the Corrib, the diapir Corrib, with the 1820-3 well. A lot of these might even be clasts of country rock that have been mobilized within the diapir as halokinesis has taken place. So this is the well database that we have. So now what I'm going to do is I'm going to take you on a tour from north to south, looking at a few seismic sections from the basin, and we're going to look at the geometries that we see and what sort of salt structures that we see. So starting up in the north, the Erris Basin is a very narrow little graben, and this is where that most northerly well is that we're going to use, the 1231A. And in this well, the Permian section is essentially, at most, you're looking at centimeter scale stringers of anhydrite in a 20-meter section of predominantly carbonates. And then the upper Triassic section, which is a second layer of potentially salt-prone sediment, there is no salt. It's actually mostly sandstone and red mudstone dominated with a lot of volcanic clastic sandstones in there. So there's not a lot of salt going on in this part of the basin. It's kind of the same story as we move a little bit further south. And here what you're starting to see is the impact that these Eocene volcanics have on data quality. So on the very right of the section, where the volcanics have been eroded off by that base or that Eocene unconformity, the data quality is actually not too bad. But once we go beneath these volcanics, the only thing we can really see are some of the brightest sediments and some of the sills that sit beneath the lavas. But in this area as well, we're looking at basement-involved faulting and not a lot of evidence for salt. Now, as we continue to move south, this is where we start to begin to see this mechanical detachment and this characteristic style of salt deformation. So here again, we have this 1951 well in the Permian section. Again, we're looking at a few meters of anhydrite and a background of carbonates and clastics, and there's no salt in the Triassic section. But as we move down dip, so northwestwards of the well location, we actually start to see our Mesozoic section being mechanically detached from the Paleozoic basement. So we're starting to see that salt content increase, and so we're sort of entering this transition zone where we're going from clastic dominated to a more salt prone part of the basin. Now moving down into southern Erris, this is where things start to get really salty. So particularly on the western margin of the Erris Basin, we actually see evidence of two salt layers being developed. So we have that upper Triassic salt and the Permian salt, and we're also beginning to see characteristic salt related structures forming. So we're seeing a Permian salt pillow forming beneath the lower Triassic, and then we're also seeing a series of very tight little normal faults soling out into the upper Triassic, forming on top of these little salt rollers. And we're beginning to see indications that where the salt pillars are forming, there might be a link to what the Triassic and the Permian salts are doing as the basin develops. So we're now going to step down into the northern Slyne area. And the most characteristic features that we see down here, there's lots of these things. There are these big Permian, very sort of long wavelength folds, big salt pillows, which most of the time have an associated Triassic salt wall or salt roller at the crest of these structures. So the one in the middle is the one we'll focus on later in the talk. This is the Corrib gas field. But you can see two other structures flanking it equally have some sort of mechanical detachment on that Triassic salt there as well. So we're well into the double-decker salt tectonics area of the study area. Moving a little bit further south now, we're in the central Slyne Basin. And what dominates this part of the basin are these high relief structures immediately abutting the basin bedding faults. So the most characteristic one here is the 2741 structure, the one targeted by that well. And what's striking here is that the structure targeted by both wells, the 2741 and the 2751, the top of the lower Jurassic section are essentially at the same elevation. There's only about 100 meters difference in where the wells penetrate that lower Jurassic section, even though one is on the basin margin and one is immediately adjacent to the basin bedding fault. So there's a little bit going on here, and this is the other structure that we'll focus on a little bit later in the talk today. Now moving a little bit south from here, we see that while we had that high relief structure with not a whole lot of erosion going on, you can see here that this same, essentially 5 kilometers southwards from that last structure, we have a very distinct angular unconformity that chops the top of the lower Jurassic off this feature immediately adjacent to the basin bedding fault. So there's a little bit more going on than just a simple monocline or British monocline, and that's something that we'll touch on in a little bit. And then the final structure that we see in the basin are these relatively simple reactive diapirs. This is one from the southern Slyne Basin. It's got lots of nice indicators of timing. So we see that the crest, there's that sharp angular truncation of the lower Jurassic against the base upper Jurassic unconformity. So we know that we're getting the reactive diapirs forming in that lower Jurassic phase of rifting, early Jurassic phase of rifting. But then we also see that it's reactivated then during the late Jurassic phase of rifting. So showing that a lot of these things has a multi-phase history to them. So putting all this together, the ultimate result is that map on the left there. And hopefully this is a useful tool for explorers in the future, so that we know where we have principally our upper Triassic salt layer, which is going to be the main seal rock for a lot of the discoveries in the future. And the implications for this are that we can now apply this for things like natural gas exploration, and also doing feasibility studies for areas that might be prospective for carbon sequestration. And then the last bit to touch on there is a better understanding of the paleogeography of offshore Ireland, which is quite poorly understood. If you look at a lot of maps for offshore Ireland or for sort of northwestern European paleogeographies, offshore Ireland, the Atlantic margin it's always just hanging off the edge of the map there. No one pays too much attention to it. So we can build in what we've learned from this basin. And what I'll actually do now is look at a few of the undrilled basins along particularly the margin of the Rockall Basin. And we can start to see that there are actually lots of indicators of salt tectonics across the Irish Atlantic margin. So the first one of these is in the Ronan Basin, which is essentially the conjugate margin to the Erris Basin. If you were to close the Rockall Basin back to its pre-Cretaceous extent, the Ronan Basin essentially is the opposite side of the Erris Basin. And what we can see here is we have a decent degree of evidence for a little Permian salt pillow immediately adjacent to that Paleocene unconformity there. I'll just turn on my little laser pointer. This feature here. And then just 2 more basins. We have the Fursa Basin here, which is just to the west of the Slyne Basin, And again, we see evidence for mechanical detachment from between the Mesozoic basin fill and the Paleozoic basement. And then we look at the Goban Spur Basin south of the Porcupine Basin, and we see evidence here for Triassic salt, because during the Permian this would have been essentially in the Variscan mountain belt and unlikely to have any Permian sediments, but we know that we have a lot of Triassic sediments along strike, a lot of Triassic salt along strike. So good evidence for it here. So these are some of the applications in terms of paleogeographic reconstruction and de-risking these drilling in undrilled basins along the Irish Atlantic margin. So what I'll do now is we'll come back to the Slyne Basin and we look at two of the structures that we touched on briefly as we were on our roller coaster tour through the basin. So the first of these that we look at is the central Slyne Basin, essentially the development of these ramp syncline basins and these high relief structures that we have immediately adjacent to the basin bending fault. So first, let's look at a few surfaces from this study, from this area of the basin. On the left, we have a base salt map, so essentially the base Permian unconformity, the top of our Paleozoic basement. And what you can see is there's a lot of quite small, diffuse normal faulting. Most of it is synthetic to the basin bounding fault, to this fault forming along here, and it's dipping to the southeast. Now, if you look at the structure map on the right, this is a sort of near top Triassic structure map, and you can see the fault families above and below the salt are very different. What's interesting here is that the majority of the faults in the post-salt section are actually antithetic to the main fault bounding the Slyne high over here. And we also can see quite clearly these high relief features that are immediately adjacent to the basin bounding fault and how they're sort of discontinuous as we go along strike along the basin bounding fault. Now, this mechanical detachment occurs across a relatively thin layer of salt. So when we're looking at fault families, there's about 120 faults mapped to the post-salt here, and of that, only 2 faults hard link these 2 faults here that cut through this top Zechstein group surface. But even so, we can see from the thickness map, there's a series of wells shown here in red, where the Zechstein group is incredibly thin. Another characteristic feature from the isopac is we see the salt thickening in the immediate hanging wall of the basin bounding fault. Now, some of this is an artifact from the fact that the salt will meet the fault plane a little bit over where the basement would truncate against the fault plane. But we can see that we have these discontinuous over-thickened bodies also slightly back from the fault plane. So there's an element of active salt tectonics here, a bit of halokinesis involved in the formation of these high relief structures in the immediate hanging wall of the basin bounding fault. So let's go back to this first section and have a look at it in detail. So I mentioned earlier about the erosion at the base of the upper Jurassic unconformity. So if we look at it in a bit more detail, in the 2751 well, this unconformity removes the base of the middle Jurassic and about half of the lower Jurassic section from this area. Whereas across next to the basin bounding fault, at the 27401 well, we have essentially a complete pre-upper Jurassic section. So we have that lower section of the middle Jurassic and then a complete lower Jurassic section. So what this is telling us is that this topography that's forming at the base upper Jurassic is a post-base upper Jurassic feature, and we can see lots of evidence for this. So we see this growth sequences going essentially the wrong way off the crest of the structure into the hanging wall of this large listric detachment fault here and onlap onto the flanks of this structure here. And then we also see that as the structure continued to grow, it eventually welded out where we have lower Jurassic and an apparent weld between the lower Jurassic and the Carboniferous basement. Now again, going slightly to the south, about 5 kilometers south of that last line, we see here the same amount of erosion that we encountered on the basin margin. So here we have removed that middle Jurassic section and some of the lower Jurassic. And it's kind of reminiscent, if we think about it, I've just sort of inverted that last reactive diaper that I showed you. So we're seeing the erosion of this crest. So rather than these features being something like a breached monocline, related to the growth of the normal fault beneath them. There may have been a series of active salt structures along this fault plane before the fault eventually breached the Mesozoic section and became emergent. Now, if we look at the wider basin for a bit more context, there's a good degree of evidence for this. If we look at the Slyne embayment together with the central Slyne basin, we have essentially the same basin fill over here. And you can imagine that if we were to restore the Carboniferous, top Carboniferous basement to the same level as over here, these Mesozoic sediments could overstep this essentially an eroded footwall that is the Slyne High. The other indicator of this is that we kind of see a linked gravitational system here. We see evidence of sort of folding compression down here and largely extension up here. So that this may have been a linked, as the basin began to tilt, you may have seen gravitational sliding from the basin margin in the southeast towards the main basin banding fault against the Porcupine High rather than the Slyne High in the northwest. Now, we see even further evidence for this if we do RMS amplitude maps in that Upper Jurassic section. This is just one from an arbitrary horizon within the Upper Jurassic, and what we're seeing here is that during the Upper Jurassic rifting, we're getting these transverse drainage systems coming off these highs here and here, feeding into an axial drainage system going through the middle of these basinal synclines, which would have fed southwards into the Porcupine Basin to the south of the Slyne Basin. What's also interesting here is that we actually have a well that drills through it, and we know that these channels represent really high quality fluvial sandstones with a little bit of estuarine reworking. And so putting that in context with the fact that we know that at the base of this Cenozoic and this Cretaceous unconformity, we actually have almost a kilometer of sediment removed, we can begin to see that during the Lower Jurassic, the initial basement structure, the initial basement banding fault may have been the one that now bounds the Slyne embayment, and that the emergent Slyne High was yet to be emergent during the Lower Jurassic. And so along strike, we get the erosion that we saw in that feature a few slides ago, whereas this feature here at the 2741 well location may have been submerged beneath these terrestrial and fluvial sediments being deposited during the Upper Jurassic rifting. Now, we see lots of models that put this into, we see a lot of sort of early stage models for this. Things like what Whitjack and Callaway have published. Stewart has a few good examples from the North Sea. And the idea here is that this might represent the sort of the late stage end member if you were to continue the movement on this fault. Now, this is kind of a work in progress at the minute. So at present, we're working with the guys at the University of Barcelona, Oriol Ferrer and friends. And unfortunately, due to unforeseen circumstances, we didn't get to go there this spring. So the plan is to go there at some stage in this year or next year, and to use this rig to test out what sort of deformation we get if we have this sort of emergent footwall block. So stay tuned for more of that. So now the second salt-related structure that I was going to touch on is, of course, the Corrib gas field. So this is, as far as our society is concerned, a very important salt-related structure. A peak demand, it provides 60% of the country's gas demand, and is currently Ireland's only producing gas field. The rest we import from the UK and further afield. The gas is stored down here in the Lower Triassic. There's about 1 TCF of gas in the whole structure, and it's developed through a subsea tieback. So there's a subsea manifold in the seabed here, and there's about an 80-kilometer pipeline that brings it to shore. And it's expected, it's going to come off plateau in the next few years, and it's expected to shut down in 2035. So again, there's this impetus to find more gas offshore Ireland. And just a brief look at the petroleum system of the structure. Our main reservoir, as I mentioned previously, is this Lower Triassic sandstone, the Corrib sandstone formation. It's sealed by the Ullin halite member, so this Upper Triassic salt, and the gas is sourced from coals in the Upper Carboniferous. So what I'm going to do now is, because it's quite a multi-level structure, I'm going to walk you slowly through the different structural levels, and we're going to break apart this structure and see what's going on and why it works. So starting at the Lower Triassic, the structure is a very simple four-way dip-closed anticline. You can see here it's slightly elongate. with the fold axis trending northeast, southwest. And we also see there's a small additional little salt core fold over here, which is a satellite gas discovery to the Corrib gas field. Now, things start to get interesting when we get up into the upper Triassic. So what we can see is there's this narrow elongate salt wall that forms along the crest of the anticline, essentially parallel, but not exactly above the same, not directly above the fold plane of the salt core fold. And with an isopack, we can very clearly see that it gets thickest towards the crest of the anticline and thins both to the north and south. We can also see that this, the yellow and halite member fills in the topography here, so it fills in this little half graben here as well. So we know that we have this very thick salt seal above our lower Triassic sandstone, so we know and we're happy that we have our gas in place. Now, when we get up into the Jurassic overburden, things start to get a bit more complicated. So when they drilled the 1821 discovery well, the initial target of the well was actually this Jurassic tilted fault block. And when they drilled the well through here, they found a series of breached oil columns throughout the section. So then they carried on drilling and found the gas in the lower Triassic sandstone. So why did this happen? Why does the gas charge remain but the oil charge does not? So if we then look at the post-rift sediments in this area, we can see very clearly that the same fault, this delamination fault here, has been reactivated both during the Cretaceous, it offsets the base Cretaceous uniformity, excuse me, and again during the Cenozoic. So it offsets these Eocene lavas, which have been dated to about 40 to 43 million years old, as well as some younger overlying Cenozoic sediments. So it's been active at multiple stages throughout the development of this structure. So in terms of preserving a gas charge while losing an oil charge, what seems to have happened here is as the relief of the lower Triassic salt core fold grew, essentially it got higher, you get continued extension on this delamination fault. And the main phase of oil charging is presumed to have happened at the end of rifting, so at the end of the late Jurassic. But what happens is you get subsequent movement on this fault during these post-rift phases of basin development related to the Rockall Basin to the northwest. And what we can see here is we have Cretaceous growth sequences into the hanging wall of this listric fault, as well as preserving a thicker Eocene lava section. So this listric fault has been reactivated both during the Cretaceous and the Cenozoic. And what's happened during these stages is that you have cross-fault juxtaposition of your really nice fluvial sandstones in this upper Jurassic section, and you lose that oil charge. But what's crucial to preserving your gas charge is that because you have that second layer of salt, this Triassic layer of salt, this delamination fault, actually, it sols out into the Jurassic salt and never actually interacts with the lower Triassic salt core fold, thus preserving the gas charge while we lose the oil charge. So this highlights, again, this is probably one of the most multi-phase evolutions of forest structure in the basin. But putting all this together, the idea is that we have this early Jurassic rifting is the initiator for the salt pillow. As the salt pillow begins to form, you get delamination faulting occurring on that second layer of salt, that Triassic layer of salt, and essentially it then becomes a positive feedback system. So as you shed the crest of the anticline to the flanks, because you have the movement on that delamination fault allows that, it allows the salt pillow to continue to grow, and so you get this positive feedback system, which is quite cool. The only problem is that it continues to work even during the post-rift phases, so you lose your oil charge, unfortunately. But we've got the gas, so that's not too bad. So we can see that these structures work very well for natural gas. They're very good natural gas storage vehicles. And they've also shown that they can be resilient, at least in the Triassic section, to post-tectonic activity. So they make very good long-term storage sites for CO2. And for CO2 sequestration, we're looking for storage periods of at least 30,000 years, if not more, to make a meaningful impact on climate change. And what's quite nice here is that if we look at similar structures adjacent to the Corrib gas field, like this one here. We again see the same geometry. So we have our lower Triassic fluvial reservoir, essentially the intersalt layer between the Permian and the Triassic salts. But in this case, we can begin to see more clearly our basement as well. So down here, we're looking at potentially second levels of pay, where we have fluvial sandstones in the carbon section. But it also means that we have essentially two stacked saline aquifers for CO2 storage. So these are very high yield, high volume structures where we can put CO2 and be quite secure in the notion that it will stay there for a very long time. And so that is all. Thank you very much. We have a better understanding of salt distribution, which I think will play an important part in future feasibility study for CO2 storage. Ireland's Atlantic margin has been significantly overlooked in this regard, but it could play a very important role in offsetting Ireland's CO2 emissions. And something that's really cool in the basin is, of course, the multi-layered salt interaction. So it's an area of ongoing research where once we do physical modeling for the central Slyne Basin, we're hoping to do something similar to this here. So keep your ear to the ground for that one. And then, of course, the implications, we are an applied research center, the implications are for natural gas exploration. And hopefully one day large-scale CO2 storage. So thank you very much.
Hey, Conor, thank you so much. I must say your drawings, your seismic sections are absolutely gorgeous. Okay, so let's go to questions. So this one is from, let's see here, Kenneth Peterson. So Conor, how do you see the future of petroleum geology research in Ireland, given the government's decision to cease all new oil and gas exploration and the resulting exodus of companies from the Irish offshore?
It's a good question, and it's one that we deal with ourselves at iCRAG most days. There's been heated discussions. So strictly petroleum research, I think there's still a very strong impetus for it in Ireland, and particularly in Irish universities, we have a lot of expertise in certain areas, particularly things like sediment tracking, reservoir modeling, structural geology, that are applicable to basins not just within Ireland. So I think if you're looking to go into research in Ireland, it will be viable long term. And at the same time, as I kind of allude to in this talk, there's a lot of overlap in what we do to find things like oil and natural gas. It has a lot of applicability in also assessing the feasibility of structures for long-term CO2 storage. So in terms of an area of technology transfer, there's a lot there. So I think it definitely has a viable future for a good few years yet.
Great. Can you provide, this is also from Kenneth Peterson, can you please provide a paleogeographic context for the Zechstein in Western Ireland and its link to the Zechstein basins in the present day North Sea, Norwegian, and NORCAP basins?
Yeah, I actually have a paleogeographic map that I didn't include for brevity, but for offshore Ireland, what seems to be the case, if you look along the European, the northeastern European Atlantic margin, is you have a series of salt-prone basins, things like the West Orkney Basin. There's evidence of salt in the Faroe Shetland basins. So it's very likely that marine ingress into the Slyne Basin and probably other basins along the Rockall margin came through, from the Boreal Ocean to the north, through the west of Shetland area, through maybe some of the basins on the other side, on the margin of Greenland. And so that's how you got that marine ingress into the area. And then what seems to have happened is that similar to the paleogeography of the North Sea, the salt seems to be deposited in areas of active extension during the late Permian. And there's evidence that there's a good degree of Permian rifting offshore Ireland at the time. So for example, in this talk, you might say that the Erris Basin, where you have that sort of 20-meter thick salt pore section that might have been, you know, a marginal area, whereas the Slyne Basin would have been an area of active extension in the late Permian. And that sort of, again, shows how complex the framework of basins is offshore Ireland. So there could be sort of an anastomosing rift. So as I kind of alluded to in linking the Ronan Basin, which was the conjugate margin, to the Erris Basin, salt ingress or marine ingress may have come through an active Ronan Basin, and then you switch polarities to the other side of the Rockall Basin. So your marine waters come sort of the one side of Rockall and the other side of Rockall, because Rockall wouldn't have existed at the time. But email me. I have some nice maps that I can show you if you're interested further, for sure.
Thank you for that. Okay, so this one is from Mark Rowan. Conor, the Triassic salt is the seal, but your source rock is beneath the zechstein. I assume charge was across areas where the zechstein was welded. Can you please comment on this?
Yep, absolutely, Mark. There are areas adjacent to Corrib where it appears that the zechstein is welded to the Carboniferous basement, particularly on the reprocessed seismic. The issue, I didn't mention it when I was talking about Corrib, but the issue again is that because you have that Eocene volcanics and then you have a very hard crystalline chalk immediately beneath the volcanics, the seismic data in the area is terrible. The seismic section that I showed from Corrib, that's actually an OBC data set, and it's still not great, even though it's been reprocessed within an inch of its life. There are areas where there is welding. There's also areas where, through just faulting, you have placed the Triassic across a fault plane adjacent to the Carboniferous basement. So you can get it both through areas that seem to weld and also from a cross-fault juxtaposition of, you know, coal-prone Westphalian equivalents with the Corrib sandstone. So I think both mechanisms could work. And because you seem to have gas in all the structures that you drill, it doesn't seem like it's an issue getting the gas through the zechstein. It seems like there's enough welds that all of the viable structures have at least a hint of gas in them.
Great, thank you for that. This is from Leo. He said, hi Conor, excellent talk, very interesting study area and beautiful data, thank you.
Thanks,
Did
Leo.
you try to quantify the relative contributions of thick and thin-skinned extension in the area? If so, roughly how much of it is due to gravity sliding relative to the total extension? Did you try to balance some of this thin-skinned extension with contraction in the down-dip anticlines and or diapiers?
Yeah, no, that's a very good comment. It's somewhat difficult to quantify because there's so much missing section, because you get that kilometer scale uplift, but there's definitely indications that it is a linked gravitational system. So particularly in the central Slyne Basin, it seems that because it's quite a steep sort of trapdoor graben, gravity has played a role in moving the Mesozoic section down dip. In terms of quantifying it, we've done very basic stuff. We've balanced a few sections on move, mainly the post-salt section. But some of the numbers we get don't make a whole lot of sense. So maybe we can have a discussion about that, as I know you're a lot more numerical in your salt science than I might be. But it's definitely something that we're looking into because, yeah, it's in terms of putting the structures in context, it helps a lot because there's a lot going on in the development of a lot of these structures. So those hanging wall structures, there's an element of it's a monocline. There's an element of, was there a pre-existing salt structure there before the emergence of that salt? You also have, you know, the geometry of the fault plane controlling the later geometry of these hanging wall structures. So imagine it's like a stack of needles and you're trying to slowly unpiece it without the whole thing falling down. So I think that definitely has a role and will make a lot of sense, I think. But it's a great comment, thank you.
Cool. Yeah, Leo just mentioned that he's looking forward to seeing the results of your physical modeling. So will that be like a second paper out of your PhD? Are the physical modeling results? Or third paper?
Yeah, so the physical modeling at the minute it's essentially a focus on those hanging wall structures. So essentially, I would have had the results to show you had COVID not happened, because I would have been there earlier in spring this year.
Yeah.
Oriel has been very understanding, and we will get these models run at some stage. And it will be a separate publication, but it'll be, yeah, hopefully we'll really pull these things apart and hopefully come up with a satisfying answer.
Cool. Sounds good. Good luck getting that set up. All right, so another question from Marcos Trenos. In several seismic profile interpretations, I have seen the volcanics to cross-cut several horizons, climbing across the horizon, so climbing and cutting across the stratigraphy. Anyway, they do not have only an interlayered geometry. Could you please tell us what kind of volcanics these are, because I'm not familiar with the area? What is the source of the volcanics?
Oh, so some of them are volcanics and some of them are sills. So the ones that cross-cut stratigraphy are probably sills. So the source is, they're related to the opening of the Atlantic and the development of the North Atlantic Igneous Province. That's ultimately their source, and they come from depth, so you can see, in some sections we can see below the salt, beneath sort of the Carboniferous section, very large sills. And so it's likely a linked system, and in some places you can even see the very large sills connected to the post-salt small sills, which then reach the surface and you get small lava flows. So it's a very sort of nice area to look at for igneous things, and I've also posted, pictures of little cinder cones and volcanoes and stuff that are related to those Eocene volcanics. The climbing things and the things that cross-cut stratigraphy are very likely to be sills, and they're related to the North Atlantic Igneous Province.
Just a question that I was wondering, have any of that volcanic activity impacted the petroleum systems? Meaning, did it help enhance it, or could it perhaps have caused it to overmature? Has anyone studied that, or is there any knowledge on that?
So the basin modeling that I've seen done, and that we did a little bit ourselves, it doesn't seem to have a huge impact on the thermal maturity of the source rocks in the area. In terms, like, most of the time the sills will interact with that upper Jurassic section, which, because of all this post-drift activity at the start, was like, when exploration started, was the target, and now people ignore it because they know that it's all this post-drift activity, and every time you drill through it, it's breached oil columns. The Triassic is king now. Nowhere has there been a sill encountered in the Triassic, so it doesn't seem to interact with the reservoir or anything. Its main impact is that you have these widespread lavas near the seabed that reduce the image quality. So their main impact would be uncertainty and interpretation beneath them. In terms of just the petroleum system itself, they don't have a huge impact on it.
Okay, so probably, and I suppose drilling hazards as well.
Exactly, yeah. You don't want to be drilling into a sill at a weird angle or anything, yeah. Absolutely.
Cool, thank you for that. We have some more questions. This is from Carlos Geraldo. Approximately slide 24, he says, how confident are we about the igneous intrusions along the seismic line?
Slide 24, okay. Let's have a look-see. Slide. So that's slide 24. So perhaps this one, this sill here, maybe.
Yeah.
So in terms of identifying sills on seismic sections, they stand out as very high, very bright reflectors. And then, as mentioned by the previous question, they also cross-cut stratigraphy. So in terms of interpreting the sills, they usually are very easy to interpret because they're so discordant with the rest of the geology. There are areas where they seem to follow it a little bit. So you might, like, in terms of, say, extending this sill a little bit further, it probably goes a little bit further than I've drawn it, potentially. Like, you could say maybe it jumps up, and that sort of high impedance reflector there could be it. I don't know. if this isn't the slide, Carlos can comment and we can talk about it, talk about the right one. But he's, yeah, again, he can email me if he has any questions about it. And if he's interested in the North Atlantic Unions province in Ireland, because there's a lot of cool stuff to talk about for sure.
Cool, thank you. We have another question from Paul Whitehouse. He says, great presentation, Conor. Are there any published physical modeling experiments that approximate what you plan to do with Oriel in Barcelona? If so, how will your experiments differ?
Great question. There are lots that are quite similar. The main difference we have is we want to look at the along strike variability, because that's the defining feature of these basins, is that because if it would be a simple, monocline, you'd expect it to be relatively uniform along the fault plane. As we can see, they're not. We also see that there's a bit of topography on the fault plane. And then locally, we also have salt that seems to sort of diaperically move up the fault plane as well. So there's a few different features. So there are ones that are quite similar. So things done by like with Jack and Callaway. One of Oriel's students, Maria Roma, did something quite similar, but she was focusing on the inversion. So if you have these features and then invert them. We're going to focus on the extension. We're going to focus on along strike variability. And so things like how does, say, a pre-existing, say if there was a salt pillow above the fault plane before the fault started, what sort of, what sort of geometries would you expect to get? Yeah. So hopefully it'll work. Like all experiments, it could go terribly wrong and we get nothing good out of it, but fingers crossed that doesn't happen.
Thank you. We have another question from Ian Davison. Do you think there is salt deposited across the whole Rockall Basin?
I think that there is probably salt in the Rockall Basin, as in like it would be a precursor, one of these precursor Permian basins that's in there. The Rockall Basin is largely a hyperextended Cretaceous feature, so it postdates the formation or the deposition of these two principal salt layers. But I think there's definitely some evidence on some seismic sections, particularly the PAD 2D lines. There's a few basins where it seems to be it's basins similar to the Slyne Basin that is slightly, rather than being perched up on a basement high, it for some reason is down thrown into the Rockall, and salt may have migrated out of that into the sediments around it. But because the Rockall Basin is so ridiculously huge, there is not a lot of salt there, just in terms of the fact that it's such a big basin. But I think there is salt in there, and it's likely migrated from basins similar to the Slyne along the margins of the basin.
We have another question coming in here from Neema McGovern. Great presentation, Conor. Do you think the igneous intrusions are localized to a specific part of the basin?
Thanks, Steve. The volcanics are definitely localized to certain areas. Now there is an element that locally there seems to be, they then get eroded by subsequent Cenozoic unconformities. So it's a question of were they much more aerially extensive and then they've just been isolated in areas where, because you can see, for example, in this slide that's shown here, there's a little bit of normal movement on the fault, and you've preserved that sort of Eocene, Miocene section beneath that then second Cenozoic unconformity. There's an element that in certain areas it is a preservational feature where they're being kept versus removed, but they're very aerially extensive. So the controls and where they're deposited aren't exactly clear. There's likely a link to these big crustal scale features, because all across the Atlantic margin, the big igneous centers that show up on the magnetic data set are all located on big basement suture zones. So it's likely that these might be the source for these igneous centers, but the volcanics are just very aerially extensive, I think.
Mm-hmm. Great. I have one more question for you. Let's hear, or do we get another one in here? I just saw it move. Oh yeah, we do. This is from Mar Morgus. Hi Connor, congratulations for the amazing talk. More a comment rather than a question linked to the restoration of cross sections discussed by Leo. Not sure if there are available thermal and burial models that could help you to estimate the amount of section missed during uplift events, maybe worthy to check.
Yeah, absolutely. So that luckily there has been there's a lot of different studies done on exhumation because it is such a big factor in these basins. So you have things like seismic velocity analysis, vitrinite reflectance, shale velocities, shale liquefaction. There's about 6 or 7 different techniques that have been used. It is very variable. So one thing that came up, particularly when I was working with CNOC last year, was that it's not a blanket sort of exhumation. It doesn't occur like the whole basin doesn't come up. It's local and it's fault controlled. So sub-basin to sub-basin and structure to structure, it's quite different. So even, for example, for the Corrib structure, if you look at there's a paper from Corcoran and Mecklenburg from 2005. They looked at the shale velocities in the wells in the footwall and in the hanging wall of this delamination fault, and they found I think it was like a 500-meter discrepancy or an 800-meter discrepancy in the exhumation. So this side was much more was exhumed further than the hanging wall of the district fault, and that probably had something to do with this late movement on the fault. So as you exhume this, you throw this is down thrown on the fault plane. But yeah, it's a very complicated uplift story. And the data at present, because it's all well-based, or mostly well-based, is very sparse. But it does show it to be a very complicated picture. But yeah, very good point in terms of the restoration, very good point. Thank you very much.
All right, and then I just have one last question for you. From a petroleum system standpoint, have anybody completed a seep and slick study to see potentially which basins are the most active in terms of the hydrocarbon production?
Yeah, so there's a paper actually published by, I think it's VIS, someone from TNO, I think it is, from 2017, and they look at seep studies across the entire Atlantic margin. There are lots of evidence. There is a lot of evidence for seeps across the area. There are lots of surface slicks. We also see, when we look at the Cenozoic section, you can see that you have layers of paleo pockmarks, and these are all related to faults, so they all occur above fault planes. So there's a very strong, and this is likely the breaching of the oil accumulations in the Jurassic during that post-drift exhumation. So people have looked at it. For the Jurassic section, it probably helps. For the Triassic section, I don't know how much it would help. But people have looked, and the ultimate sort of, if we were talking, if you were a company looking at this basin and saying, do I want to farm in or not? The broad picture is, if we're looking at the Jurassic section, very high risk because you have this post-drift reactivation that breaches a lot of the structures. But if we're looking at a Triassic prospect with a salt seal and no clear evidence of welding or a fault cutting right through the middle of it, you're probably good to go. So that would be how you would risk it. The seeps, they've helped, but I think people, I don't know, they're good, but they're not great, personally.
Thank you so much for that, and thank you for presenting. We really enjoyed your talk, and I'd just like to open it up to any of the other panelists before we disconnect.
Yeah, thank you very much for the invite, guys. Very much appreciated.
Conor, thanks. This was fantastic. I'm really interested to see what more work comes from your dissertation.
Hopefully it lives up to expectations, Tim. Thanks for the invite. Cheers.
Thanks, Conor. It was a very, it's an amazing presentation. Thanks a lot.
Thank you, Clara.
Cool. Thank you so much, everyone. And we'll be back in 2 weeks. Jill Apps is going to be giving the next talk in 2 weeks. So we hope to see you then. In the meantime, feel free to get a hold of us at aapgsaltbasins@gmail.com. Thank you guys. Take care.
Thank you.